Hello everyone, we're Group 18. Our project is about electric transportation. And each of us will make a short presentation about background information, battery system, renewable energy, and application in Iceland. And now I'm going to tell you about the environmental problem that caused by oil. Okay, so oil is one of the most used energy in modern days after the Industrial Revolution. When oil is burned, it will cause the rise of CO2 concentration in the atmosphere. From data here, prior to the Industrial Revolution, the concentration of CO2 is around 218 ppm. However, in 1986, the concentration became 350 ppm. And by the time 2015, it is estimated to be 400 ppm. And the rise of concentration can cause global warming, which is a serious environmental problem. In terms of food supply, increasing frequency of hot days will bring about more intense heat waves. Also, warmer temperature and higher CO2 level can accelerate the amount of pests, fungi, and weeds. And all of this can cause trouble damage to agricultural products. In the case of fishery, global warming leads to higher sea temperature and lower amount of dissolved oxygen, which will support the growth of algae. And this will cause the malfunction of marine ecosystem as well as fishing industry. Global warming also causes tropical and subtropical disease to spread to cooler places, which can become a threat to medical system, such as dengue fever, Lyme disease, and West Nile virus. All of these are fatal disease to humans. Last but not least, the rise of sea level is also an issue caused by global warming because of melting iceberg and glacier. From 2019 to now, you will see the sea level has increased for around 8 inches. And what's worse, experts estimated that in the coming 2,000 years, the sea level will rise for around 2 meters. And from this picture, when the sea level rises over 6 meters, nearly 15% of land may sink under the sea, which is a paradox against to the sustainability we are advocating now.
We're speaking about the battery and the system. In current forms of electric transportation, the most common one is the lithium-ion battery. The anode is made of carbon and the cathode is made from lithium cobalt oxide. Lithium undergoes oxidation, producing electrons, which goes on to power the whole vehicle. In our model, we will be adopting a lithium-air battery. The difference between the lithium-air battery and the lithium-ion battery is the composition of the anode and the cathode, and also the lithium-air has a completely different energy density compared to lithium-ion. So how does a lithium-air battery work? The essential way is lithium in the anode undergoes oxidation, producing electrons, and these lithium ions goes on to join with the oxygen at the cathode to form lithium peroxide. And this lithium peroxide deposits on the carbon cathode. Why use lithium air instead of lithium ion? Essential thing is the energy density. Lithium ion has 160 watt-hours per kilogram, while lithium air has 1,700 watt-hours per kilogram, and gasoline has 1,700 watt-hours per kilogram. The first challenge with the lithium-air battery is the lack of a uniform carbon cathode with well-defined pore structure, which doesn't give the manufacturer control of what reactions, depositions, and decompositions that happen on the cathode. So to solve this, we have adopted a three-dimensionally ordered mesoporous carbon structure. A 3D-ON carbon has well-defined pores and good uniformity at the nanometer scale level. So we are increasing the surface area, increasing the rate of the reaction. Another challenge is the products of the side reactions, other than lithium peroxide, are often found to deposit on the pores of the cathode and is difficult to decompose upon recharge, leading to fast capacity fading. As you may see, there's a bare carbon surface, a surface with lithium peroxide deposited on it, and then there's the surface with byproducts clogging up the pores. What we have done is applying a thin uniform layer of iron oxide throughout the carbon cathode. This results in the enclosing of the carbon surface while keeping the important pores available for lithium peroxide decomposition. The enclosing of the carbon surface provides the desired protection that should minimize side reactions inherent to the carbon surface. Another problem with this lithium-ion battery could be the carbon's affinity to react with oxygen during discharge, causing the cathode to wear off and capacity to fade. So for this, once again, the iron oxide protects the carbon surface from reacting with oxygen. Another problem would be the uncontrolled formation of lithium peroxide, which results in the need for greater recharge potential, reducing efficiency. As we all know, carbon is known to promote the reduction of oxygen, which in turn results in the uncontrollable formation of lithium peroxide throughout the cathode, which makes it hard to decompose lithium peroxide for us. So once again, what our solution is, the iron oxide will hinder the ability of carbon to carry out the uncontrolled reduction of oxygen and formation of lithium peroxide, which may seem to defeat the purpose of the battery. However, this actually controls the reaction progress. Once again, iron oxide is an oxygen evolution reaction catalyst and can ensure the complete decomposition of lithium peroxide, preventing the capacity from fading due to lack of decomposition. In order to compensate for the reduced oxidation reduction reaction activity of carbon, we have adopted the introduction of palladium nanoparticles, which is a good ORR catalyst in aqueous and non-aqueous electrolytes. So this is the final structure: palladium, iron oxide, and the carbon pores. Another problem is lithium anode reacting with the electrolyte and wearing off. What have we done to solve this? We have adopted, we are going to coat the lithium anode with a solid electrolyte called Lisicon, lithium superionic conductor. It is a mixture of lithium, zinc, germanium, and oxygen, and has a very high conductivity. The layer is ionically conductive and prevents vigorous reaction with water, protecting the lithium anode. And finally, the electrolyte. For the electrolyte, we have adopted a LiTFSI salt electrolyte. It is lithium bitrifluoromethane sulfonimide. It has increased lifetime, high capacity gains for long battery life, and improvement of cell capacity after storage. As you may see in this graph, this is the normal electrolyte, which is used in current batteries, whose capacity continues to fade. But just by using 30% of this particular electrolyte, it has increased by 80%. And as you may see over here, it surely shows that our electrolyte is far better than all the currently used electrolytes. Another problem is the usage of pure oxygen in our battery. For this, we have adopted an oxygen selective membrane at the point where the oxygen comes into the battery. This prevents water vapor entry and entry of other unnecessary substances. So finally, the most important goal of our model is to increase the cycles of the battery before its discharge potential drops to a useless small value. Keep in mind that our battery was only exposed to 500 milliampere hours per gram, which is less than 10% of the maximum capacity of 6,000 milliampere hours per gram. If you look at it, a bare 35 nanometer pore size 3DOM carbon cathode failed after the 16th cycle. With addition of palladium, it failed after the 31st cycle, and the final product with iron oxide failed after the 68th cycle, which means when you apply 6,000 milliamperes per gram on the maximum end, it will surely fail after around 800 cycles, which is more than the current lithium-ion battery used in the Tesla model. And with that, our battery, this battery will be used in the future electric transportation.
Then now let's move on to discuss the situation of oil. Some experts suggested that oil is going to run out very soon. So we need to figure some solution to solve this problem by replacing the old type of car which used gasoline to a new type of car that uses renewable energy. And in the next slide, we're going to look at the difference between 4 types of car, which are electric car, compressed air car, gasoline cars, and hydrogen vehicle. First, we compare the first 2 of the car. By looking closely at the stats, we can easily figure out that the digits of the electric car is way better than the compares their car. So we can say that electric car has a relatively better performance. And then now let's move on to discuss other part of the cars. Actually, you can see that they have very similar performance. Electric car has a better power, but it has a limited maximum distance. And then let's look at the refill time. The refill time is still, it's not going to be a problem of electric car because we can just swap the entire battery of the car, and by this we'll reduce the time of the refill to refill the battery. Okay, and then let's move on to look at the cost of the car. Electric car has the highest efficiency of energy, but it doesn't cost very much. You can look at it's probably a third of the cost of the BMW, so I guess everyone can afford it. And then most importantly, electric car yields 0 carbon dioxide emission, which is very environmentally. And by providing a benefit of on the environmental side, it can also save you a lot of money without buying gasoline every month. So considering all the factors, apparently electric car is the best solution for us to discuss later.
Talk about renewable energy. So from the graph, you can easily show that the global trend in electricity production is almost 4 times over 3 decades. And this is world fuel share of electricity. So you can also easily see that the coal and oil are the main source of energy in these days. And from this graph, we can show that we produce energy using different kind of area, and we use high voltage transmission to transport it to different kind of sectors like energy sector, transport, industrial, residential, commercial, and agriculture. But now we don't use the oil to do that. So now this is renewable energy wind power. This figure shows that the energy power produced by per wind power generator is about 10,000 kilowatts with a radius of 150 meters. In the future, it is likely that the energy power will have an increase, reaching the number of 20,000 kilowatts with radius of 250 meters. And the second picture exhibits several types of wind power generators. And this is about solar power. So we estimate that we will have 3.9 times 10 to the power of 6 joules per year, but it is just theory. So it is like we cannot do the 100% conversion efficiently. And this is the dam-tied hydropower. By opening the water gate, using the water gravitational potential energy to drive the turbine in order to generate electricity. We convey the electricity power through the long-distance power lines. And this is tidal hydropower. It's very similar to the slide we used to we talked about in the last slide. So it's through making the rotor rotate, we generate electricity, and this one is through the float moving up and down, we generate electricity. And this, now we are talking about geothermal energy. We can also use geothermal energy to make electricity. A geothermal power plant works by tapping into steam or hot water revolves underground. The heat is used to drive an electricity generator. So from this graph, you can also see it has a lot of potential.
And now in the next part, we're going to apply our electric car to Iceland. First, let's have a look at the basic information of Iceland. It has a population of about 329,000 of people, but with a high level of car ownership, about 747 cars for every 1,000 inhabitants. We consider about 4 main advantages of Iceland: wealth insurance, government support, a large green energy producer, and well-developed new energy, renewable energy. Let's first talk about the wind power. Data shows Iceland had a great potential of wind power and a hydropower as well. Maybe it's because there is a drift around Iceland making the hydropower possible. And the graph shows that the geothermal energy of Iceland almost ranks the 7th out of the world, which is very, very great. And in the following pages, we'll try to attempt to make some acceptable prediction in terms of today's information we have already gained. First, the population. You can see through the years, it's almost a smooth growth. So we make such prediction in 2025. And then the car ownership. There's an interesting thing. There's a bankruptcy happened in 2008, which may have some connections with the bankruptcy, which may result from the too fast growth before. So we prefer to predict a smooth growth in the coming years. And the electricity consumption, also you can see a smooth growth. And the last, electricity loss. There's also an interesting thing. Around 2010, there's a volcanic explosion in 2010. Because of that, it may lead to more loss of electricity that year. So maybe we just ignore that data. Here are the information and prediction we have already known. And also we assume that 15,000 annual miles of travel with 50% city and 45% highway driving. First thing, we need to calculate how much car in 2025. And then calculate how much electricity we need for one electric car, about 5,500 kilowatt hour. And together this and the electricity loss, we calculate the total amount of electricity we need. Then compared to 2012, we need about more than 42.27% more electricity than now.
In conclusion, knowing that transportation with oil is neither sustainable nor a future tendency due to the depletion of oil supply and the increasingly serious environmental problem, we choose to substitute the power supply from unrenewable oil to other kinds of renewable energy. To apply the renewable energy to practice, we have selected the lithium-ion battery, which can be used as a media for future transportation and replace the gasoline medium, such as electric cars. After making analysis to the situation, we found that Iceland is the most ideal place for us to apply our project module, hoping a further application to the whole world.